Legendrian maps.
So thank you very much. Thanks to the organizers and to the audience. So I hope to have a lot of fun today. This is a fun topic. I should be able to draw a lot of pictures, and there's going to be a lot of combinatorial shadows of deeper theories, but I'm really going to stick to the combinatorial shadows and not talk as much about the deeper theories. Okay, so this is joint work with Linyi Chen, Crider-Philips, Braeden Reinoso, and Natalie Yao. When this started, they were all of my undergrads. Braeden is now almost finished with John Baldwin up at Boston College. So we let this live for a little while, and then Braeden and I came back and worked it out. Okay, so the objects of interest today are exact Lagrangian fillings of Legendrian knots. So let me just quickly. And let's just work with Legendrian knots in the standard contact. In the standard contact R3 for today. And what I mean by that is, let me sort of give you a definition by picture. So I'm going to look in the symplectization of the standard contact R3. So here's R3 and alpha. This is my 3 manifold. I'm going to have a knot, a Legendrian knot sitting inside my 3 manifold. Quick poll of the audience: do I have to would you like me to explain what the heck a front diagram of a Legendrian knot is, or should I? Excellent, good. I don't have to. Well, I was looking at you. I wasn't. Good. Okay. And then we're going to work in the symplectization, which is R cross R3 with the symplectic form D to alpha. And I want to look at exact Lagrangians that are cylindrical over the Legendrian sort of at positive infinity. So if this is lambda, we're going to let this be, well, how about t to infinity cross lambda, and then are just some nice exact Lagrangian inside inside the symplectization. I'm going to let my Lagrangians be either orientable or, because of the title, possibly non-orientable as well. Okay, that's supposed to be a cross cap. Let's see if, but whatever. Okay, and let me just give you some more a bit of motivation, a bit more of the setting. So let me tell you a little bit about orientable and then non-orientable fillings of these puppies. So okay, so if I have one of these nice orientable fillings, then in that case I can compute the Thurston-Benneken number of the Legendrian knot simply from the Euler characteristic of the filling. So in that case, I get TB of lambda is just minus the Euler characteristic of L. This actually is, and if you're curious, I can prove this to you in like 5 seconds flat. In the non-orientable case, well, you can get there's a similar formula where you can compute the TB, the Thurston-Benneken of the knot at sort of the knot at the boundary to be, again, minus the Euler characteristic of L. But now we have to sort of add in the normal Euler number of the filling. And for those of you who haven't seen the normal Euler number of a non-orientable surface, basically it's just it's the obstruction to sort of pushing the pushing the surface along the normal bundle without intersection. And so it's what its name suggests. Okay. Even better, in the orientable case, such a Lagrangian filling actually computes the 4-ball genus. It actually minimizes genus across all across all surfaces that bound the knot. So in this case, the 4-ball genus of sort of the smooth knot underlying lambda, which I'll still call lambda, is genus of L. Okay. And hopefully we'd be able to write the same thing over here, but I have absolutely no idea whatsoever if this works. Sort of the right question. So the right question to ask. G4 is just the minimal genus of all surfaces whose boundary is the knot in the 4-ball. Right, minimal. Okay. And I really don't know what to do here. What you should do, what you would love to happen, would be for L to minimize sort of the 4-dimensional cross-cap number of all non-orientable surfaces whose boundary lies on the knot. I've got a lot of evidence that it works. I've got sort of evidence and examples that it works, but the proof is much harder.
So what would you like to put there?
Yeah, I'll write it down. What I'd like to do is to say that, say, the cross-cap number would be the minimum overall smooth surfaces, smooth non-orientable surfaces. I do want to. The right way to say it is you do want to that sort of have the same normal. Or you want to restrict the normal Euler number before you try to minimize. You don't want to try to minimize over all possible normal Euler numbers. Yeah, but I don't. Again, there's evidence for this, but I don't know how to prove it. Basically, this comes from an adjunction inequality, and adjunction inequalities sort of famously don't work for non-orientable surfaces.
What's the cross-cap number?
So just first Betty number. Okay. Just think first Betty number. Right. Exactly. It's just the number of P2 sum M's. Sure. Yeah, exactly. Okay. Another reason sort of to do this restriction is also that usually these, well, actually not usually, theorem. These non-orientable surfaces non-orientable Lagrangians can only realize sort of finely many normal Euler numbers, whereas smoothly you can realize all of them. You can realize all of them. All right. Okay, so let's continue sort of this dichotomy. All right, so here there's a well-known upper bound for the TB of for the Thurston-Bennett of a knot sort of a smooth knot given by the Humphrey polynomial. And in this case, if you have an orientable surface, then the Humphrey bound on TB is sharp. And the same thing for a non-orientable surface, then you get to the Kaufman bound. Humphrey tends to sort of see orientation. Kaufman sort of sees less orientation, so it's not surprising that you get one or the other. And then the final fact about orientable things, and this is that so if let me write it this way. It's just that the smooth knot underlying the Legendrian knot has to be quasi-positive. Now, what does quasi-positive mean? You can think there's a couple of ways to think about it. Sort of from the Braid theoretic perspective, is that there's a Braid representative that's conjugates of positive generators. That's one way to say it. Another way to say it is that this is the intersection of a complex curve. not I'm sorry, a complex analytic curve, like a holomorphic curve with the four ball. Those are actually equivalent conditions. Say again? The link, no, smooth curve. Link of a smooth holomorphic curve. Yeah, links and singularities are much more restrictive, I think. Yeah. And on this side, it seems that it's actually, I mean, so you sort of lose the connection with complex geometry that you implicitly have over here. And once you lose that, and once you lose that connection, sort of all heck breaks loose, right? And in fact, sort of the motivating question for today really is, so given some Legendrian in R3, right? How does the existence of a non-orientable Lagrangian filling restrict the smooth knot type? So again, sort of on the orientable side, at least you know your knot has to be quasi-positive. That's a fairly restrictive condition. And again, the motivating question is, well, what would be the analog of this quasi-positivity condition for non-orientable fillings? Okay. Mm-hmm. So what do they look like? Oh, just like what the bound is it looks like? Yeah, sure. So formally they're the same, so it doesn't really matter. So the way what the bound looks like is, so you'd say if sort of lambda is a Legendrian knot with it's with underlying smooth type K, then the TB of sort of the TB of the Legendrian knot is bounded above by the degree in the framing variable of the Pomfrey polynomial of K minus 1 or something like that. But so the Pomfrey polynomial is sort of is a two variable polynomial. So A counts the framing. You just replace with Calvin polynomial. Yeah, exactly. Okay, other questions before we move on? And this is supposed to be this is supposed to be the framing of the talk. So if this didn't make sense, then well, that's it. Go. You go. You can go ahead and go home. All right, good. All right, let's do it. Okay, so the rest of the talk will proceed in three parts. I'll give you some constructions and examples, and with sort of a theorem that I want to sort of sketch how to prove. I'll tell you a little bit about the techniques underlying the proof, which are the taking of normal rulings, and then I'll just sort of tell you how to finish off the proof. Okay, so let's start off with some constructions and examples. And the first construction, and I'll attribute this to is well known, that says that if you have Legendrian isotopy, zero handles, by which I mean taking nothing and going up to a lovely Legendrian unknot, and one handles, by which I mean going from, say, a pair of cusps, and then attaching a one handle along that core, where you sort of end up with that puppy as the co-core. All of these induce Lagrangian cobordisms. And further, let me sneak a definition into the proposition that Lagrangians produced sort of using these moves. We'll just call these decomposable. And now I'm going to secretly assume that everything we do is going to be with decomposable Lagrangian cobordisms through the rest of the talk. Open question: is every Lagrangian cobordism with non-empty top and bottom decomposable? Seems kind of amazing that that's still open, but
wait. So what is the? Could you say one more time? What
yeah, just the constructed from sort of constructed by a sequence of these of these elementary cobordisms.
Okay.
Whether every Lagrangian cobordism between non-empty Legendrians is decomposable. Probably not, but because there is a non-decomposable cobordism from this puppy. So that's sort of the twice stabilized, not to the empty set. This is Francesco Lin. I think this is like an undergraduate summer project of his, actually. That's yes. Yeah, so this is a non-decomposable. I mean, it has to be. It has a max. But with both non-empty, again, probably not. But right. So smoothly, there better be a two-handle. Right. Smoothly, there better be a two-handle. Well, but decomposable for in intervention 3, decomposable only allows just isotopy 0 and 1, no 2. This is not part of the decomposable. This sort of set of moves that you're allowed to do. Okay. By the way, just one quick note: this isn't a two-handle. This is actually a genus 2 surface. It's a pain in the butt of a construction. It's cool, but it's a pain in the butt of a construction. But just because there has to be a two-handle, that's it. They just sort of smoothly there has to be a two-handle, so it couldn't have BTC. Yeah. Oh, I'm sorry. I must have misunderstood your earlier question. Sorry. Yeah. Okay. Let me give you a quick example because this example is going to come up later on. So let's start with. I'm just going to take up the whole board. All right. So let's start with nothing. Let's add a 0 handle. Let's do some isotopy. Cleverly to make it look like this. I think I did that right. Okay, good. And you'll notice that if we orient this, and then try to put a 1 handle across that core, that's actually going to be a non-orientable handle, right? because the orientations don't sort of properly match up as we go through. But nevertheless, this will give us a lovely trefoil line. In fact, this is a Mobius strip filling of the trefoil. This is a negative trefoil. With a little bit of imagination, you can see that this will work for any minus P2 torus knot. Just few more twists here before you join them up, and that'll give you any minus P2 torus knot. P is the number of twists. Well, P is the number of crossings. Yeah, half twists actually is the right way. If you want to be anal about it, it's half twists. Yeah, Jordan?
Can I go back to this open question you said one more time? So just,
Yeah.
Is it true that if you just allow, if you allow two handles, then is it obvious that it's true?
But the question is, what is a two hand? What is a?
Is there? Oh, I see. Is there no natural?
There's no natural two handle here.
Okay. All right.
Right. There's no natural two handle to write down. Yeah. So somehow, if you sort of take a slice, take a slice of a Lagrangian that's coming into a max, it's not you can't sort of Legendrianize it. The best example to think of is take the Whitney immersion. At the bottom, so when you're coming up to where the intersection point is, that growth, those kind of look Legendrian-ish if you take a slice. But the top, when they're coming down, if you sort of take slices, those look sort of anti-Legendrian-ish. The crossings are actually look like reflections of Legendrians in a sense. That's not a technical term. That's a vague. Yeah, we'll just sure. Again, I didn't mean that's not a real definition. Didn't mean to make it. Yeah, it's purely a heuristic thing. Absolutely right. Okay, so let's take this and let me state two theorems. The second one, I think, is the one that I'll concentrate on. I just want to give you sort of a sense of the geography of these things, like going back to the motivating question. So I'm trying to build from the inside as instead of trying to restrict from the outside. So for instance, an alternating knot has a non-orientable filling if and only if it's not positive. And by the way, somehow this is supposed to be a smooth knot, and it's supposed to be like a symplectic thing. So what I mean by this is that an alternating knot has a Legendrian representative that has a non-orientable filling, if and only if the original smooth knot was not a positive knot. And this might get you thinking, oh, maybe sort of too much positivity gives you orientability. By the way, that's true. Positive knots all have orientable fillings, and maybe just everything else, right? Maybe it's the complement. And then then we sort of take inspiration from this and start looking at torus knots. So let's take P bigger than Q bigger than 0. I want knots, not links, because the theorem actually would change with links. So it turns out that the positive ones are orientably fillable. But not non-orientably. Well, we just proved that these negative P2 are non-orientably fillable. We're sort of marching on our merry way down this, positive orientable, negative non-orientable, until that's supposed to be a negative sign, by the way. Oh, a positive knot is just one that has a diagram with all positive crossings, with all sort of right-handed crossings. As you wander around, it has a diagram so that as you wander around the diagram of the knot, it goes over, under, over, under, over, under. I should stop using that definition because there's like a really good geometric condition now, but I cannot remember it off the top of my head. Okay, but then as you sort of wander further into negative torus knots, suddenly these have no fillings. This one's actually easy. This is because the Kaufman bound isn't sharp. And then, oops, I did that backwards. I'm sorry. No, -b4n. No, I got it right. These also have no fillings. And this is somehow, this is what the proof of this is what I'd like to try to get at for the, to try to give ideas for the rest of the talk. Sort of how you show that sort of negative torus knots, even negative torus knots that are divisible by 4. You note the missing 4n plus 2 case. I don't know the answer to that, although I'm pretty sure the answer is no. Are actually not fillable. Okay. But what this is pointing to, again, going back to the motivating question, is how hard trying to figure out what are sort of the topological types underlying topological knot types underlying these non-orientably fillable things, because somehow the old in the old orientable version, somehow this quasi-positivity, somehow some kind of generalization of positivity is for what you want to get your hands on. It's not quite full. But it's not too positive, right? It's not too positive, but it's not too negative. Somehow it's somewhere in between. And and not too positive and not too negative is pretty much the best that I can really do right now. Right? I mean, this talk isn't really meant to give you full answers to hard questions. This is supposed to raise interesting questions for further exploration. Okay, so let's talk about a little bit about techniques for proving that last bit of the theorem. Okay, so the technique is these things called normal rulings. And these are combinatorial structures on front diagrams that secretly are, there's sort of secret shadows of things called generating functions, sort of generating families for the underlying knot. No, I secretly used one. Where did I use one? I secretly used one. Oh, when I was mumbling about this and saying that somehow you only want sort of finitely many. You really want sort of that only finitely many Euler numbers can normal Euler numbers can come up. Sort of the right. Well, a good way to prove that is to use this ideal isomorphism between the linearized contact homology at the boundary and the homology at the filling. And basically because you can only, there's only going to be finitely many linearized contact homologies, then you're only going to get finitely many like topologies of the fillings, and so that's fixed. There are only finitely many of these, so there are only finitely many of these. So I use the DGA sort of is in there. Finitely many augmentations. Well, the dumb way is that over Z mod 2, you're only there's only finitely many possibilities. Yeah. I'm sure there's a slicker way, but that's good enough. Yeah. And so the advantage of DGA techniques over the ruling techniques is that whenever you use DGA techniques, you can sort of erase the word decomposable all over the place. For these, I need the word decomposable all over the place. Okay. Right. So anyway, so these guys are going to be sort of combinatorial shadows of sort of generating families. For Legendrian knots. Let me also answer your question another way. Secretly generating families basically contain the same information as linearized DGAs. So these rulings are close to, not quite. If you're curious about what not quite means, I can make that specific later. Close to, but not quite the same kind of information as augmentations of the DGA. So I'm sort of, if you're curious, I can explain that later. If I did that now, that would be the talk. Okay, so here's the definition. So this is sort of and somehow these are also sort of closely related to sheaves, and you can explain that later to everyone else. All right, so here's the definition. So a normal ruling of a Legendrian knot, let's call it rho of a Legendrian knot lambda, is just a set of crossings, which we'll call switches. So that when you resolve the switches, you get a link of unknots, and that link of unknots has to satisfy some properties. And I'll call that link of unknots lambda rho, so that three things hopefully happen. So first of all, each component of lambda rho it's not just an unknot, but is the max TV unknot. Secondly, exactly two components are incident at every switch. So we can't sort of have a component sort of pinch back to itself. And thirdly, right? So you can imagine that around a switch there can be sort of different the components of the components can have kind of different configurations, so they can look like maybe that so that somehow they're disjoint here. You can imagine they look like that. That's fine. That's they're this one, the green is nested inside the blue, or you can imagine that they're sort of interlaced like that, and you want to ban these. Okay, so you're allowed to do this and this, but not that. And let me give you some examples. So again, think of these like kind of like disks. Here the disks are disjoint. Here the disks are nested one inside the other, and here they're neither disjoint nor nested. Okay. Secretly, this has something to do with how if you take a Morse complex and you pass through a switch. That's something to do with how the handle slides change the yeah. Yeah, that's exactly right. This is Dmitry Fuchs's name for him. Although if you look carefully at like stuff that Yasha did in the early 80s, these are somehow secretly there. Yeah, let me give you an example. Let me also say one more thing. So if the crossings are all positive, it's orientable. We'll call the ruling orientable, and if they're not all positive, it's not orientable. Okay, so we'll say that so positive switches mean they're either like this or like that. Yeah, that's exactly, yeah, that's the easier half of the theorem I'm going to state. Yeah, that's exactly right. So yeah, examples. Do I do it here? Where am I? I'm here. Let's do examples here, even though I erased this. All right, so trefoils. Trefoils are always good ideas. So let's do everyone's favorite trefoil. And there are actually exactly 3 rulings of everyone's favorite trefoil. Those aren't downward cusps.
They're just
they don't exist.
Oh, okay.
They're just me drawing. So the notch sort of passes through, but it sort of changes color on either side of the. Yeah. How about this? They're an artifact of how I'm drawing these.
Okay. There's nothing might mean.
They mean nothing. They don't exist. They're not there. Okay, and these are actually these are the 3 normal rulings of the trefoil. In particular, you couldn't have. You think, well, so here and here's the switch, here's the switch, and all 3 of these are switches. And you might think, well, if I can switch on the one side, this side, and this side, maybe what happens in the middle, and then you'd end up with this. Non-examples are also good, but here, when you have this switch, then your then the ruling disks are interlaced. So this is not possible. Okay. All right. So okay. So theorem. This is sort of a 2-parter. The first part is sort of the theorem of Tronoff and Pushkar, which is sort of the number of rulings is an invariant. Here, I mean, oriented, or sort of the total number, or secretly there's. I can refine these to include some kind of grading information that I'm not going to tell you about because I don't care about it today. Are actually invariants of Legendrian isotopy. The graded version is actually a nice and effective version of invariant of Legendrian isotopy.
You don't have to quantify anything?
No.
Wow.
It's just count them. You literally just count them. Yeah. Well, it's like some of so this is parallel to the number of augmentations is an invariant, but this is much easier. Yeah.
Each of these is their own augmentation. You don't have to quantify anything.
Well, okay, so secretly, no, that's not true. So these are secretly 2 augmentations, and that's 1 augmentation. There's not a 1-to-1 correspondence between rulings and augmentations.
But you're saying those 2 could you're saying these 2 rulings each correspond to 2 augmentations.
Correct.
I see.
That correspondence, the ruling augmentation correspondence. That's like, I'd love to talk about that. It's a longer answer. Mm-hmm. Right. So all right, I'll give you a shadow of an answer. Okay, so so rulings are somehow a ruling is giving is extra information on top of a surf diagram for some family of functions that generates the knot, right? But if you want to record homological information, the surf diagram isn't enough, right? You also need to record the handle slides. And so if you included all of the information, sort of all the handle slide information, then you actually get a 1-to-1 correspondence between augmentations and sort of rulings with handle slides. But the rulings themselves, so there's an ambiguity about which handle slides you can sort of sit inside the surf diagram and give you what handle slides would give you the surf diagram. That's where the many to one instead of 1 to 1 is coming from. The intuition, so the intuition behind that was actually my one and only grad student, Brad Henry's, but really sort of based off of ideas of Pushkar. The many to one correspondence is an old theorem that Lenny and I proved when we were really young. So if that was surprising, the really surprising half of this theorem is actually Dan Rutherford's thesis. No, sorry, the paper before this is something that Dan Rutherford did before before his thesis, which is actually if you organize these number of rulings, and they actually appear as coefficients in sort of pieces of the Humphrey and Kaufman polynomials. Well, actually, in fact, a to the minus tb minus 1. In the Humphrey polynomial, this is for the orientable ones, and in the Kaufman polynomial, if sort of somehow the total orientable and non-orientable together sort of appear in the Kaufman polynomial. So somehow the point is that these two are not just Legendrian invariants, but they're actually smooth invariants. They're actually invariants of the smooth knot. Somehow, like sort of via this Legendrian theory. This proof is kind of mind-blowing, actually. Oh, so a ruling is orientable if all of the switches, like here, these are all orientable. If all of the switches are positive crossings, and it's non-orientable if it's not, and totalist means either non-orientable or orient, just both of them together. So the Kaufman doesn't see whether it's orientable or not. The Humphrey does.
Wait, so it's actually an invariant of smooth?
It's actually an invariant of smooth isotopy. Yeah. The fully graded version is an honestly Legendrian invariant. You can tell the Chekhov examples apart, for example.
Is the same thing true?
I agree.
Is the same thing true if you introduce this extra data that you need to get it to be the same as the augmentation?
Oh, no, because somehow this number of rulings literally is you can organize them into a polynomial, and then that polynomial literally is the coefficient of this in Humphrey. Somehow there's like not much more information that you can get.
Yeah, I have more questions.
Okay, I might. You're getting. I'm suspecting that I might be saying that's a great question when you ask them later. Yeah. Okay. So this is sort of showing it's like relationships between Legendrian or smooth isotopy and rulings, but not really for Lagrangian cobordism. And in order to get relations to Lagrangian cobordism, we need to introduce sort of one more thing. And this is somehow the cleverest definition in the paper. Okay, so we're going to let rho be an orientable ruling. Of your Legendrian not lambda. And then we're going to define the resolution linking number of lambda with respect to the ruling rho to be the following. Just sort of take this resolution, so take this like link of unknots, and just compute the pairwise linking numbers and add them all up. Okay. So this is sort of the sum over all the pairwise linking numbers is sort of inside the resolved diagram. Secretly, this is also you can also read this out of the Humphrey polynomial in sort of the oriented case. I have not given you the tools to see that, but So that's the oriented version. The unoriented version so if you're not necessarily orientable, then you can define the mod 2 to be basically the same thing, except here my components naturally have an orientation. In the unoriented case, they don't. You just give them any give it any old orientation, doesn't matter, because mod 2 it doesn't matter. So now again, we're just going to take the sum of the linking numbers. And again, these are sort of oriented anyway, and these sort of come with natural orientations. And then the theorem, actually, if we want to quickly, we can quickly calculate. If we quickly sort of move over here, you can see that for this one, the resolution is secretly a hop link. And in fact, it's a positive hop link. So here, you'll get RLK is 1. Same with this one. And for this one, well, they're just disjoint, right? So you get RLK 0. I'm trying to say it's super simple to compute this. And then the theorem, and I think Julian anticipated the first half of this theorem, or Augustin, I can't remember who's, one of you two anticipated the first half of this theorem a little while ago, says that, well, if we have a, so if L is a decomposable Lagrangian cobordism from say lambda minus up to lambda plus, and we start off with a ruling down at lambda minus. Then sort of the two parts, the anticipated part was, and there exists a canonical ruling at the top that sort of comes from the ruling at the bottom. See it? You follow the cobordism, and there's like the isotopic invariance sort of tells you how to do it. The isotopy and then the 0, 1 handles, you just look at it, and there's only one ruling that could. There's only one way the ruling could change. This theorem somehow is noticed by, I think, so Pan and Antoponrat noticed this part of the theorem a little earlier. So there exists a canonical ruling, say rho plus of lambda plus, and then we sort of added on the idea that this ruling is orientable if and only if L is. Okay. And then the second part is that, in fact, this resolution linking number is an invariant, is invariant from top to bottom. So and I'll put a 2 here. So the mod 2 one is if L is not orientable, then you have to work mod 2 as opposed to not. Unsurprisingly, you have to work. We have to work mod 2 for non-orientable stuff. Okay, and then sort of if we go back here, the consequence is that these two can't be rulings that come from a filling, right? Because they would have to be. This one can and does come from a filling, but these two cannot be the rulings that can't be the rulings that come from the filling. For those of you who know, there's actually at least 5 fillings of the trefoil. So in a sense, they're all coming from this one. They would all imprint this one at the top, and the other ones sort of have to be. There has to be some crazy isotopies going on the way up. Okay. Oh, okay. So that's a good question. And there's sort of a roundabout. There's a couple of ways to. Well, let me ignore the RLK part, but just this part. You mean? Yeah. I'll mumble about this at the very end. But about this part. So right. So the DGA, you get a map, and if you have an augmentation, there's a corresponding ruling. Right. So ruling, augmentation, map. It's not. Maybe it's true. I haven't worked through the details. Maybe it's true that they're the same thing, but there's no reason. There's no a priori reason for them to be the same. So it could be a different correspondence on the way up.
Like you would actually need the whole, like if two augmentations correspond to the same ruling, then
right.
the pullback augmentations also correspond to the same ruling.
Exactly.
So
yeah.
I think maybe that's not so clear.
I mean, you need some really super careful work to make that happen, and I have not been sufficiently unlazy to do that super careful work. Oh, the correspondence or the no, it's so the original proof is it's actually some pretty careful combinatorial work. It's not easy by any stretch. Yeah, some pretty careful combinatorial work in there. Okay, so here's one application of the theorem. Let me sort of finish off by let me just go straight to this one. Let's talk about sort of how we would use that theorem to prove that say sort of negative torus knots with even negative torus knots with that where sort of Q is divisible by 4 don't have any fillings. For those of you watching pedagogically at home, that was some awesome board work that you just saw there. Okay, so I can do some certainly less than 5. So here's how it works. So actually, until the very end, this will work for any even Q, actually. Any even Q, yeah, any even Q. So it turns out that the Kaufman polynomial that there actually exists a unique there's a unique ruling of a front diagram of this. Someone worked very hard. Yokota worked very hard to tell you what the Kaufman polynomial of a negative torus knot is. And then you just compute. Then once you have that ruling in hand, you can just sit down and compute. The mod 2 resolution linking number, and you see that you get 0 if Q is not divisible by 4, and you get 1 if Q is divisible by 4, and so bingo, not fillable. These are also probably not fillable, except when Q is equal to 2, but I don't know how to prove that. All right, so let me just end with just by mentioning a couple of possible next steps. So there, I kind of already told you what these next steps are. So the first thing is to try to actually prove that cross-cap minimization idea that Lagrangians actually do minimize the cross-cap for a fixed Euler number. Somehow to do that, you'd have to find your way around the adjunction inequality, around the non-existence of an adjunction inequality for non-orientable surfaces. And before you say, but you can just take double, like orientable double covers. No, you can't, because those things are not going to, you can't embed them back as Lagrangians actually. So the second thing would be to try to refine this non-orientable RLK, this RLK2, to an integer invariant that really takes that somehow is that secretly what's going on is the RLK2 is only seeing the Euler number mod 2, the normal Euler number mod 2, well, mod 4. And if you can sort of see the normal Euler number sort of on its nose, then you can lift this to an integer invariant and then maybe sort of figure out what the hell's going on here. Right? The other way to do it is instead of just trying to think through that, you could try to turn this into try to find this in the contact homology. This is Augustin's earlier question, is you just to try to find this somewhere in the contact homology, the ungraded contact homology. I talked to Pan and Dan Rutherford about that. There's maybe some hope to do that, but it wouldn't be easy. Yeah, because well, I can ban the orientable fillings in because the Homfley bound isn't sharp for any of these. There can't be, so that sort of takes away. I don't need to use this. So to get rid of the non-orientable, this is the way to do it. And then the last question, then the last next step is really just what's the proper, going back to the earlier motivating question, what's the right conjecture? What smooth knots should have Legendrians with the Legendrian realizations with non-orientable fillings, and that's somehow breaking free of complex geometry, and trying to figure out what the analog would be. Right, so thanks for all your questions. Really appreciate that, and I'm all set. I'm happy to take more.
So this thing about the rulings being a topological invariant, I'd never heard that before.
Mm-hmm.
So
it's completely crazy.
So okay, so then is it true that like, is there any way you could show that augmentations are also like, so not like, first of all, is it true? Probably not, I guess. Because I guess you have I mean, is it possible that the augmentations are that the same thing is true for augmentations?
Maybe. I mean, there's a bunch. So these conjectures are so old that I think only Lenny and I remember them. Is that a lot of the material in sort of a lot of the contact homology material works only when is only sort of effective when you have gratings around, right? Well, there's two places where they're effective, either when you have gradients around or if you very cleverly use the non-commutativity. And when you abelianize and ignore gratings, or even just take mod, even just either you abelianize and ignore gratings, or abelianize and just take mod 2 gratings, those tend to those really look like they're topological invariants. And so somehow the symplectic, Legendrian, whatever contribution is really coming in A in the gradient and B in the non-commutativity. And that would include augmentations, would be part of that. Now, how to prove that, how to count them properly, I mean, I don't know. But those are sort of old, I guess those are old conjectures that I don't know anything about. And so now this is the answer to one of those, to one of those. Although now I'm thinking, sorry, I'm wondering if this is actually sitting in a paper, secretly sitting in a paper of Pan's, and she didn't realize it, because you can compute the augmentation. Oh no, sorry, sitting in a paper of, oh God, Lenny and Vivek Shende and Dan and Steve Sivek. It might be. the previous paper, the augmentation, counting augmentations by, I can't remember what the name of it. It's a paper about counting augmentations whose name I cannot remember. It's the paper before the augmentations or Xi's paper. And there they can sort of compute certain counts of augmentations over finite fields by looking at the ruling polynomials. And if you sort of erase all of the gradings in those, then you might be able to get back that somehow augmentations over z mod p or something are smooth invariants as well. I'm not sure if that's sitting in there. I'm also not sure if that's true, because they might need the gradients to do what they're doing, to do what they did. But maybe. Yeah. Mm-hmm. Mm-hmm. They have to. You have to use the word decomposable everywhere. Yeah.
I guess you also said that something like for those three rulings, two of them correspond, each correspond to two different applications.
Mm-hmm.
Third one corresponds to. I don't think that the five different rulings.
Right, that's how you prove it. And this actually, thank you for saying that, because this actually I think connects to a different discussion we were just having about if these correspondences correspond. That's somehow an indication that they don't.
I
That's actually yeah. So thank you. I think that can answer Augustin's earlier question. Whether if you sort of whether the decomposable ruling correspondence corresponds to like sort of taking a ruling, taking its augmentation, using the DGA map, and going back. I think the answer is no. Right? I think this actually shows that the answer is no. Yeah. It doesn't.
That example shows that the answer is no.
Yeah. So the ruling augmentation corresponds to say there's two augmentations here, two here, and one here. But the fillings are all here. So.
But what does that? So what does that say? That says that you're saying all the fillings.
So all these fillings are decomposable too. I think they are. Yeah. All the fillings would imprint this ruling at the top.
But wouldn't that just say that those are the only ones in the image? Okay.
Because if they did, there wouldn't. Yeah. This the easiest possible example already would. Well, okay, fine. Aside from the unknown, the easiest possible example already does it. There's something weird going on there. Yeah. I mean, it's coming from the rule. It's coming from the ruling augmentation correspondence. That's not that natural. Of course, you have to do a lot of combinatorics to make that work, and those combinatorics. It's not surprising those combinatorics wouldn't be geometric. How about that? I'm gonna have to think about. That's a great question. I'm gonna have to think about that a little bit more. Yeah. Okay. Yeah. I'm trying to think of a way to explain this in finite time. It's well, just so I've literally it's complicated, but I literally gave a talk about this. I don't know, like 13 or 14 years ago. I think I was at Penn even, and I was. And I remember introducing the talk by saying, "Don't do like to all the graduate students in the audience. Don't do this. Don't prove anything like this because like it was combinatorics without geometry, right? And like good combinatorics comes from geometry, right? Good combinatorial invariant of Legendrian knots. Let me.
I agree with that. You shouldn't tell that to the authority.
Well, but they're answering different questions, right? So if I specify it as good combinatorics, good combinatorial invariants of knots come from geometry, then I feel I'm a bit safer. Well, I just realized this is being recorded, right? So I should be really careful that I do not want to insult. I really don't want to insult the field of combinatorics in this. But I genuinely don't want to do it. But in a sense, like good combinatorial proofs in this field should have some underlying geometry to them. And that correspondence is not one of the places that does that. Like each individual piece does. Like I mean, there's good geometry and analysis behind this invariant. That's fine, but the correspondence doesn't have that have any geometric feeling. If you can produce a filling from certain rulings, right? You can't. I mean, you can't do this. You can't produce a filling from this. I mean, the prehistory of this is that. Okay, so if you remember back on this board, there was a sort of statement that that if you have an orientable filling, then your knot is quasi-positive, right? So that's not an if and only if. So for symplectic fillings of transverse knots, that's an if and only if. That's a result of Boileau and Revkov. And somehow that means symplectic with transverse, if and only if complex, if and only if quasi-positive, right? That's not true for Lagrangian fillings of Legendrians. There are examples of quasi-positive knots, like the 820, for example. Just why not? The 820 is an example of a quasi-positive knot that does not have a Lagrangian filling. Even though if you sort of take a transverse push-off, then you get a perfect good symplectic filling of it. So question: when the hell does a knot have a Legendrian represented with a Lagrangian filling? And conjecture, probably not true. Conjecture would be quasi-positive and the Hopfli bound is sharp. But the Hopfli bound being sharp means then, by Dan's result, that you have a ruling, and that conjectures are based along the hope that if you have a sufficiently nice ruling, whatever sufficiently nice means, then you can sort of fill it off. And this is sort of saying how careful you have to be in order for that in order for that to work. So it's probably the Hopfli bound is sharp, and you need to know something about the coefficients of the Hopfli bound, and then maybe. But again, even that's I wouldn't bet on that being true. But yeah, but your question is actually, I mean, I tried to do that for years. It doesn't work. Proof. Yeah, if you want to solve that, the original orientable question, great, please. I'd love to know it used to be I wanted to solve it, now I just want to know the damn answer.
Great. Let's thank our speaker again.
Okay. And I want to thank the audience. Thank you for all the great questions. I really appreciate it.